And this was a mantra for his life, and I wish that each one of you will go back home and will think about good SNARKS are here needed, and at some point we're actually going to have good SNARKS and a lot of improvements. I'm Nicola, and I work at Protocol Labs, and Protocol Labs we work on a set of protocols to improve, upgrade the internet infrastructure and make it more decentralized. We've been building IPFS and Filecoin and LP2P, and this talk is mostly related to the Filecoin proofs and some lessons that we've learned and some things that we would like to use, we would like the ecosystem to develop. The talk is going to be a bit high level, but we can dive into the details later on. And maybe it's not going to be too fast. What I'm personally, I guess this is a shared feeling amongst most of you, is that we want to build decentralized services, which is different from traditional services where there is one entity that we trust to offer that service. But what does it mean to offer decentralized services? First of all, it means that there is not one entity that we directly connect to, but there might be multiple entities. And we might not necessarily trust each individual one, but we distribute trust amongst them. And sometimes we don't even distribute trust because we move the trust from trusting a particular participant in a protocol to trusting that the mathematics behind proofs are correct. And so the intuition here is that trust doesn't, it's not that we are avoiding trust. We're just transforming trust from trusting one entity to trusting some mathematical implementation, some mathematical application, or changing the trust model. And the idea is that if I want to delegate some computation on a platform like Ethereum today, I can ask, the trust model is that 51% of the network will execute and will agree that that computation at that particular output. And that's one very particular trust model, and asking all the Ethereum community, all the Ethereum miners to run some computation, it's actually really expensive, and we're trying to change different trust assumptions. And there are systems like TrueBit where we want one of M nodes that run the computation to be honest. But the graal here that we're all looking for is, can we completely remove trust assumptions and move into trusting cryptographic proofs? And these cryptographic proofs are for any type. The idea is that we use cryptographic proofs for proving that a service was offered correctly. And I want to quickly dive on how Filecoin uses these intuitions and how how our two proofs work. And then I want to generalize it to other type of services where the service is offered in a verifiable fashion. Filecoin, at the core of Filecoin, we have two ideas, and I'm not here to talk about Filecoin, but more on how we can generalize these ideas. One is storage-powered consensus. We would like to run a consensus blockchain where we don't vote based on stake, we don't vote based on wasteful work, we don't even vote, the miners don't vote based on wasteful space, but they should be able to be proportionally elected to mine on the next block based on some useful data that they are storing. So a proof of replication is basically like a proof of space, but instead of filling our hard disk with random data, we can fill our hard disk with useful data. And we can use this proof of replication even in other use cases beyond Filecoin. Let me give you an example. We can use it as an anti-spam mechanism that says, if you really want to send me an email, then you have to prove that you're storing some web pages or Wikipedia on your machine. And the second part is the decentralized market for storage. And in Filecoin, we want miners to prove that they've been storing files through time so that the client has a guarantee that they actually are storing the files. Proof of replication is, we can think of this as a proof of stake, as a proof of space, and the idea is the following, is that I, as a miner or as a prover, should not be able to lie about the amount of space that I'm using, or also prove that I'm storing some data that I agreed to store ahead of time. And there are different attacks. For example, I cannot be pretending to be multiple identities. I cannot just rely on someone else storing my data. And I cannot know of a smaller function which can generate large amount of data. Like I cannot store 100 terabytes of pi, which I can easily generate, and pretend to be storing 100 terabytes of something that I am not storing because I can easily generate. And we have this idea of a proof of replication, which is a prover, once commits to storing some data, they run a very slow encoding of the data, which we call replica. And at the time that prover is asked to generate a proof about storing a correct encoding, then the proof step is going to be fundamentally smaller and faster to execute than running the replica. So basically, I can spot someone that has not been storing the replica or has not generated the replica from someone that has the replica with them on their own. And this diagram should explain that a malicious prover will have to rerun the replica and then generate a proof. And the theory behind this, I'm going to walk through this very high level, but I want to give you an example on how you can use SNARKS for compressing proofs and not necessarily for generating proofs. Our proof of replication, our novel proof of replication works on some work that Ben Fish and others have been working on in the past few months. And the idea is that we rely, in order to have a slow encoding, we need to do a sequential steps so that we cannot parallelize these steps, or at least parallelization will not help. It will still take some amount of time. And there is there's a special type of graph that ensures that there is a particular, these are called depth robust graphs, and they ensure that there is a particular set of dependencies that will force you to do sequential computation. So what is a proof of replication is basically getting the data, encoding it in this graph, and then encode every single node on the graph by using the parent nodes. And so if every single time we need to use the parent nodes, then we are doing some sequential computation. And every single time we encode, when we do the encode step, the encode step is a tunable, slow hash function, and that allows us to say how long the generation of the replica should take. But basically, we have a graph, we put the data in the graph, we encode the graph in a very slow way, and then we take a Merkle tree of the encoded data. And then what we do, we ask, and that's the sealed step, that's the setup. And then approving time, the prover is asked to show that they have a node and the parents of the node, and Merkle trees of the challenge nodes and the parent nodes. And this is like a standard proof of inclusion, and the verifier verifies that the nodes that they received belong to the Merkle tree, and both from the encoded graph, from the encoded replica, and from the replica and from the original data, and the verifier should be able to run exactly that particular step for the challenge node very efficiently. So this should also sound very familiar because except one particular step, this is pretty much what the Zcash circuits are doing. And this is a big improvement from our previous construction. And how do we use SNARKS? Well, we don't just ask for one challenge in the graph. We don't challenge just one node in the graph. We challenge a lot of nodes in the graphs. And it would be surreal if miners have to put more than 20 kilobytes or actually larger inclusion proofs and leaves on chain. So what we do, we use the verification algorithm, and we encode this. We write a circuit that is basically this verification algorithm, and the prover now runs a proof and prove that they have verified their own proof correctly. And then this proof is basically a proof that the proof of replication proofs were correct. And the proof of replication is basically a proof that you have encoded the data properly, and then that's mostly used, that's not used to check that someone is storing your files. This is basically to prove that a miner is not storing more data, is not storing less data than the data that they claim they're storing. It's basically our proof of space that we use in our consensus protocol. Then on a separate side, we have another proof, which is called a proof of spacetime. And the idea behind the proof of spacetime is basically the following. I have a storage provider, and this could be used also beyond Filecoin. We have a prover. We have a storage provider that says that agrees that they're going to store our files, but they look like the the miners from the presentation from Coda, and they're really ugly or upset all the time, and or they can misbehave more than being upset. But the idea is the following: is that I want to check that they're storing files through time. So I would be asking them to generate a proof of retrievability every 10 minutes, for example. But say that I don't want to ask them. I would like to delegate this to some form of a quorum of people, a set of people, or a blockchain. Then I would like the miner to just post this proof on chain. But posting this proof on chain every 10 minutes, it will be, although they might be short, it might be really expensive. In practice, this requires, for if I'm going to ask them 100 proofs throughout the day, then they will have to communicate either with a verifier or to the blockchain 100 proofs, and they will have to not just n interactions, but also the size of the proof will be n. So can we do better than this? And the idea is that if we have a way for which the prover can prove that they've generated a proof, they waited 10 minutes, and then they generated another proof, and they waited another 10 minutes, then the prover can just give us the set of proofs for each individual challenge that, the prover will be generating this proof every 10 minutes, will aggregate all of these proofs, and will send all of these proofs at the end to the verifier. And the idea here is the same intuition as before. Can we aggregate and compress these proofs? And there's a lot of details to be discussed in here, and we don't have time in this presentation, but I would love to discuss with you later, which is we basically we make a proof of proofs that proves that the miner has, the storage provider has been proving all this data correctly, and instead of giving us n proofs, they only gave us one. And all this proof of retrievability and the proof of spacetime and the proof of replication are very similar in spirit to the circuit of Zcash, and we've been exploring the space of libraries to implement our own proofs, and when we ended up writing most of our proofs in different libraries, the two proofs in different libraries, and in particular recently with Bellman, especially because we made our proof of replication and our proof of spacetime really similar in the spent circuits of the new sapling from Zcash. And we have an RFP program, and it's a research for proposal, and we've been asking for academics and non to tackle these problems in different ways, and we had run this program for the first time in the past month, and we had incredible applications, and there's Evan in the audience that's been leading that project. Please reach out if you're interested to know more about what are the open problems in improving these two proofs. Let's take a step back and let's think, yes, this is interesting for Filecoin, but what have we learned that it could be used elsewhere? What we're trying to build with Filecoin, and what other groups from blockchain space have been trying to build, is this idea of a verifiable market. A verifiable market is basically like a market, but we don't really trust either the market that makes the exchanges, or we don't necessarily need to trust whoever is giving us a service. So we're basically the verifiable markets are a new shape of markets where trust is, we don't necessarily trust the service providers, but we trust the proofs that the service providers give us. So as long as there is supply and demand, and there's a way to match the orders between supply and demand, and as long as we have a place which could be centralized or decentralized that performs the settlement whenever they see the proof has been generated, and as long as the service can actually be proven, because I expect that there will be services that are going to be too difficult to prove, or physical services which are difficult, if not impossible, to prove digitally. So an open question on how can we build verifiable markets for physical services. But the idea here is that this is like combining the fair exchange problem with verifiable computation, and so as long as I have a proof, and this proof is valid, and so it gives us some completeness and some guarantees, then we can perform the exchange. And the fair exchange problem basically says that an exchange between two parties that doesn't have a trusted party cannot operate unless there is trust involved between the two parties. And the idea is that in the spirit of like Filecoin or other protocols, the client deposits their money with a third party, and then the prover generates a proof that they offered the service to the third party, and the third party releases the coins. There are more optimistic ways to do this, and there are ways to do this off-chain, and we don't necessarily need SNARKs for this, but we can rely on other type of assumptions. We can just rely on the majority of the participants in a blockchain protocol. We can rely on trusted hardware. We can rely on a multi-prover, refereed multi-prover in true-bit fashion. And, or we can have rational assumptions and use more interactive protocols and so on. And then there is this neat idea, which I don't know if it will make sense beyond Filecoin, but the idea is that in proof of space-time, we prove that we've done some work, meaning stored some files. What if we can combine different types of work? So for example, I proved that in the morning I stored your file, in the afternoon I got a signature from someone, and later on I did something else. Now, instead of posting all of these proofs on-chain, we can just post the final proof that we've done all the work that we were required to do. Maybe this is a new idea for some off-chain contracts, and spoiler alert, you can do this with in the same way that we're doing proof of space-time, but also we have nice primitives that like verifiable delay functions and also slow time hash functions that allow you to do this. And in the past week, there have been 3 papers on that, which is exciting. Now, SNARK wishlist. So as soon as we started writing SNARKs, we realized that there are hundreds of different, there are a few libraries, and we think that we can write circuits like this, and at the very end, you end up writing a lot of C++ code. And there is no Uncle Snarky that is going to come and help you out whenever you have a problem, because most of these libraries are undocumented and everything is starting now. So if you have free time, or if you're looking for good projects to work on, there is a lot of work to be done in the space, especially on tooling. And we would like to simplify the way we write circuits. And in practice, the majority of circuits that we end up writing are not low-level circuits, but are using gadgets that someone else or ourselves have implemented in low-level. And I understand that low-level circuits, so for example, SHA-256, it better be manually optimized. But the idea here is that whenever we use it, we don't rewrite it. We just re-import it with other libraries. So what we really need is a DSL or a glue that help us glue different gadgets. And I think projects like Snarky and Socrates have shown a very good direction in that. And then how do we make sure that circuits are correct? I would love to see, whenever we write circuits and arithmetic circuits, it's really difficult to analyze them. It would be ideal if we can think through them more properly, more formally. And there is a lot of different groups implementing the same circuits multiple times, and it would be beautiful to see some form of library of circuits. And then one very important thing is that whenever you write SNARKs circuits, you want to use SNARK-friendly operations, so like in Zcash from SHA to Peterson, but there are also other number theoretical cryptographic primitives like MyMC and others that we really need to understand whether they are secure or not. And if they are secure, then they would give us a lot of performance advantage. And it would be great if we could if the community could put bounties in this type of problems. And then I guess I've been talking about a few of these, and this basically, I could go forever here, but I would like to end it here saying that come to the workshop later today, where we're going to discuss with different implementers, different ideas on how do we go about writing circuits. Thank you very much.